So, we're recording. In our last very exciting biomedical signal processing class, we talked a little bit about how to do a spectrogram for an EKG. Sometimes I call it EKG because the K is German for cardio, and that's what I'm used to hearing because I used to watch television with General Hospital, and they always took an EKG, so that's what I call it. So there, but it's really ECG in English. And what you want to do, I think, is you want to go on the web and you go into my papers. And if you go into my papers, what you kind of do is you go to the DocJava website over here, my home page, and you go over here where it says papers, and then papers, and then reprints. And under journal reprints, you can see that there's a whole bunch of reprints which basically kind of cover what's in the book on steroids. So it's the same material in the book presented a slightly different way. And it's in 6 parts, and it terminates in cross-correlation, which we haven't done yet. It also talks a little bit about spectrograms. That's what we did last week. Talks about spectral leakage, which we haven't done yet, and that has to do with windowing functions that Brian just asked about. It talks about the power spectral density and some of the derivations behind what's called the fast Fourier transform. Now, when you use the spectrogram algorithm for the midterm, you may not have realized this, but you were using a fast Fourier transform. And if you hadn't used a fast Fourier transform, you'd probably still be computing it. That's how slow the slow Fourier transform is. And what I'll do when I talk about the Fourier transform is I will very glibly talk about it as though it could be continuous or could be discrete. But when you do it on the computer, it's discrete. And when you do it on the blackboard, it's probably continuous, unless you're trying to explicitly express the discrete Fourier transform. And the difference is going to be whether you use integral or summation. Moreover, when you talk about the Fourier transform, the discrete Fourier transform, you're not talking about one algorithm. You're talking about a whole class of algorithms. And that class of algorithms can be done in a wide variety of different implementations. And those implementations can vary depending upon what your application is. And sometimes people get real picky about what their application is. And you could have Fourier transforms that work with what are called integral powers of 2, or known as the radix 2 Fourier transforms, or you could have some that work with powers of 4 or powers of 8, and they could be far more efficient depending upon your application. You could have some that work with complex numbers, like most standard Fourier transforms do. You could have some that don't use any complex numbers at all. The alternatives would be the Hartley transform, which gives you the same result but in a different form, so you don't have to have complex numbers. And if you think about it, complex numbers are a big deal. And I'll tell you why. If you have an image is consisting primarily of red, green, and blue colors. And those colors are packed into 8-bit quantities. Now let's take a Fourier transform. You take that 8-bit quantity and you promote it to a floating point quantity. And it's not just a floating point quantity, it's a complex quantity. You could say, okay, big deal. You got 1 pixel, red, green, and blue, 8 bits each. Maybe that's 24 bits per pixel. But now if you convert it to 32-bit quantities, 1 for red, 1 for green, 1 for blue, now you got, well, perhaps 4 bytes for red, 4 bytes for green, and 4 bytes for blue. But wait a minute, now you got to make it complex. So now instead of having 4, 4, and 4, which comes to 12, you've got to have 24 bytes per pixel. That's a big deal, because sometimes a camera has more than 1 million pixels. Sometimes it has like 10 million pixels. And if you have 10 million pixels and you're using, like, I don't know, pick a number, red, green, and blue, right? 4 bytes each. 12 times 2, because complex, is 24, and now 24 times 10 million pixels. Hey, wait a minute, that's 240 megabytes and that's just one image. And now you got to do computations on that with some filter that's probably of the same magnitude. That's another 240 megabytes. You can say, "Hello, Professor Lyon, what are you worried about? RAM is free." I say, "Yeah, okay, but now we're going to do it with HDTV. And it's an image sequence, and it's coming at you at 11 megabytes per frame. And now you're going to do what? Make it into big complex numbers and expand it by a factor of 3 to 1 or 4 to 1? This is a big deal, especially when you figure it's coming in at 60 frames per second. A big deal for any CPU. So there are some things you have to think about when you start to go into the complex number domain, especially if that complex number domain is floating point, especially if you started in a fixed point domain. Now, when you do the A to D converter coming in off of the microphone, it's almost always fixed point, because you're getting an A to D converter and it's maybe 10 bits per sample, and at 10 bits per sample, that's giving you a number that ranges from 0 to 1024. You could use maybe at worst a byte and a fraction for that, right? Because it's probably 10 bits. But if you wanted to do it upright and do 16 bits per sample, you're only using 2 bytes per sample. Now you tell me, oh boy, I want to do an FFT and I want to make it into complex. Now you got to use, floating point numbers, and you have to use 2 of them for each sample. Big deal. So as I see it, the Fourier transform is really trading space for time. And the reason why it's fast, especially the fast Fourier transform, is because there are a few different algorithms that make use of some interesting mathematics. Let's see if we can get this going. So let's talk a little bit about some of the proofs. This is called Part 2, the Radix 2 FFT. And this is kind of our first sort of formal looky-loo at the fast Fourier transform. And the goal is to make use of the fact that you're going to have an integral power of 2 on your samples. And if you don't have that, you're going to pad it out with extra blank space or silence. And then what you're going to do is you're going to express that as a vector. So here's the vector where n is an integral power of 2. Here it is in the continuous time domain. That's just an integral that's done with a kernel that consists of a complex number expressed in frequency. Is that big enough in the back? You can see that, right? Yeah. So then if you think about it, to turn this into a continuous, from a continuous time function into a discrete time function, you change your integral to a summation. So in fact, when you look at these two, and it's rare that it's so clean, but in this one particular case, if you take that integral and put in a summation and then multiply by 1 over n in order to get yourself a unitary transform, that means you're going to have output that ranges from 0 to 1, then you got a very clean parallel development with respect to the continuous time and the discrete time. And so that's clear. And then if you're going to do this for every single value of k, where k is equal to all the different frequencies that you get from each frequency bucket, then you've got a problem, because now you've got to do a doubly nested for loop, which is why it takes order n squared computations, which is what makes a discrete Fourier transform a loser of a algorithm, because order n squared grows very rapidly. That's quadratic growth. That's no good. So we're going to knock that square term right off using what's called the Cooley-Tukey algorithm. And the Cooley-Tukey algorithm makes use of what's called the Danielson-Lankos lemma. And Danielson-Lankos lemma makes use of the laws of the exponential. And the laws of the exponential say when you multiply two bases with a common, two exponents with a common base, the exponents add. So what we're going to do here is we're going to divide up the sequence, the input sequence, into an even part and an odd part. This w to the k represents the complex exponential, where the k part is the part that appears as a multiplier in the exponent. So that's kind of a shorthand notation where we're factoring out the constants. So as it turns out, if you can break up the Fourier transform into odd parts and even parts, you basically are using what's called a divide and conquer algorithm. You're saying take all the even samples and put them here and take the Fourier transform, and take all the odd samples, put them over there with a constant, and use the Fourier transform. And if you add them together, you're going to be able to get the original Fourier transform. So keep breaking up the long number of samples into little subparts, and eventually what you're going to get is a Fourier transform comprised primarily of odd parts and even parts. You can recursively subdivide the long sample length into odd parts and even parts, odd parts and even parts, odd parts and even parts, until you get something that's really small. Then it has a trivial Fourier transform, and then you can reassemble it. You could say, well, that could be a recursive algorithm, but native recursion, when implemented in any modern language, requires that you have an automatic variable created every time you re-enter the recursion. So recursion is not going to be your most efficient way to implement this algorithm. But it's certainly a way, and it will work. A lot of times people see divide and conquer algorithms. Can anyone think of a place where you might have seen a divide and conquer algorithm before?
I think it's superposition.
Superposition? I'm not sure if that's... Yeah, maybe so. How about another one? Something from data structures. Did you guys ever take data structures? Did you ever hear of quicksort? Quicksort's a divide and conquer algorithm. What happens is you take the left-hand side and you sort that, and you take the right-hand side and you sort that, and before you sort it, you see if it's really big, and if it is, you split it again with recursion. There's another one called merge sort, which is kind of similar, and that'll also work with recursion. So that's divide and conquer. So if you look at it this way, I can get simple indices. Multiplying j by 2, I can get all the even numbers. Multiplying j by 2 and add 1, I get all the odd numbers. And now when you take a look at v sub j, I got v sub 2j versus v sub 2j plus 1. So that's giving me the even numbers on one side and the odd numbers on the other side. And so that gives me a quick way to give you odd and even. When you work through all of this, and it does take a little work, what you do is you get a mechanism that lets you keep cutting your length in half until it becomes trivial. Here it is graphically, and that kind of makes it seem a lot easier. You take all the even numbers, you put them on the left. Take all the odd numbers, put them on the right. Now take the even sequence and take the even chunks of the even sequence, put that on the left, and the odd chunks of the even sequence, and you put that on the right. Now if you just do the Fourier transform for the little two number chunks, you have what they call a decimation in time transform. So you take those, you do your Fourier transform on even chunks, and then you have to reassemble them. Well, that sounds like a pain. How are you supposed to, first of all, decimate that efficiently, and then reassemble it efficiently? Well, here comes the really brilliant, insightful part. There's a mechanism inside of a Fourier transform called bit reversal. And what bit reversal does is it takes the bit pattern and it inverts it. It takes, like if it says 0, 1, 1, 1, 0, it'll flip it around and make it 0, 1, 1, 1, 0, which sounds the same forward as it does backwards, but in general that's not the case. And so what you want to do is you want to find a mechanism in place that's going to take a sequence and reverse it. So if this is ABC 0, 0, 0, then the reverse is going to be CBA, also 0, 0, 0. Here it is 0, 0, 1 becomes 1, 0, 0. So what you see here for n is represented by 4, because 1, 0, 0 equals 4. And here what you see 2 becomes 2, that's alright. 3 becomes 6 because 0, 1, 1 becomes 1, 0, 0. That's what bit reversal does. It flips the bits around. Here 100 becomes 001, so a 4 becomes a 1. So you can decimate using this, I'll call it decimation in time algorithm, if you're able to do bit reversal. And here's how you would implement that in Java. And what this does, I don't know if you're familiar with the notation, this here is a left shift, and that is a right shift. And so you take your number and you keep shifting it left, and you assemble the bits until you obtain the reversed bit. And that's what bit R does. So the input J will be flipped around bitwise until it returns some new bit reversed number. In fact, I have the implementation for that. You can find bit R in the code. Find in path. Just put in bit R. It's very popular. And there's the bit reversal. That's a 32-bit reversal. In fact, it looks very similar to what we had prior to this. I got bit reversals for shorts, bit reversals for ints, bit reversals for strings. You need bit reversals, I got bit reversals. I got bit reversals up the wazoo. I think this will work. Let's try it. Yeah. So if you take these bits and you put it in and reverse it, you get those. So the bits go in and the bits come out. Let's see if we can check 7F. Let's try another one. Pick a number. You, pick a number. Somebody. No?
AA.
Well, 7F is 128. Let's try AA and see what happens. I have a feeling you want to have something that's a little bit less than 7F. How about if we do 6A? So now 1101010. Is that right?
Yeah.
Because I see, oh, maybe you have to start with the 0 here. I think so, because then it becomes 0 1 1 0 1 0 1 0. So I think that's correct. It's pretty cool, actually. So you can do the bit reversals. So the cool thing about bit reversals is they will do a decimation in time if the index that you are inputting as you go from 0 to n is bit reversed. And then you sample the input signal by using the reversed bits. That'll do a decimation in time. And it'll let you swap, let's say I, with the bit reversed version of I. And if you go through the entire length of the array divided by 2, it'll do a shuffle with bit reversion. And that does decimation in time, which is pretty cool, actually. So let's see now. Here is some more exponential manipulations, and eventually what you get, I think I'm writing this out using Euler. So if you know Euler, it's e to the I theta equals cosine theta plus I sine theta. So here theta is this big humongous number up in the exponent here, and then that ends up dropping down into the arguments of cosine and sine. I'm not going to ask you to do this proof, but I just thought you'd like to say, you know, this is one of those things that you can prove. You can use recurrence relations that'll let you do the same thing. And I'm running this proof by real quick because I think most students don't really care to look at proofs, but if you are one of the people that do, it's all there for you. Let's see what else we got. At the end of the day, you're going to see equations like this embedded in the code. And that's one of those things where you say, geez, where did that come from? And how did you get that? And what does this mean? And why can't I change it? And the answer is, well, it came from working through this equation. It's actually also in the book. And it's one of those things where when you see it in the code and it talks about equation 23 and equation 24, it's coming right out of the paper, so that you can go back to the paper and see where it all comes from. So what I'm kind of doing is I'm going to show you how to drive the car, but I kind of wanted to show you what's under the hood too. And that way you don't have, to treat the whole thing like a big sort of box where stuff goes in and stuff comes out and you don't have to know how it works. Because I think it's real important that you do know how it works. So when you look at like one of the FFTs in, I think it'll be in the transform package under Fourier transforms, you're going to see that stuff. And you're going to wonder, geez, where did that come from? And the answer is, Danielson, Lankos, here's that bit reversal we talked about before that does the decimation in time. Somewhere in here we're going to see, right, there's the exponents, the real and the imaginary part, and we're going to do the computations there. And now check this out. Here's equation 623 and 624, and it's all in there. So when you see that sort of thing in the code, and he says 623, 624, that should be consistent with what you see here, equation 23 and 24. It's there. So, you look at that, and I don't know, I could probably copy it and then go back to the code, and maybe what I'll do here is I'll just say / enter, paste, and now we can compare it, and gee whiz, looks like it's the same thing. Pretty much, right? Almost identical. So when you're looking at that stuff and you're wondering, geez, where the heck did that come from? And I'm citing the equations off some paper you don't know about, I could probably, if I had half a brain, you know what I'd be doing here is I'd be saying something like copy I don't know, / enter, paste. That's there. Documentation on demand. So it's not just in the book, it's also in a paper. And you can see the the notation might be slightly different. Notation's a constant battle with this stuff. And you try to be consistent with the standard notation in the field, but that's not always easy. And so what you do is you do the best you can. And sometimes notations change. Sometimes people like to use frequencies instead of radians per second. I'm really partial to frequencies, especially in a one-dimensional signal processing course. But if I move to image processing, I might want to change it all over to radians per second. And it's really all the same thing, but I like to think in terms of frequencies when I'm running a one-dimensional signal processing thing. So I thought I'd sort of point that out. There's this stuff in the code that you'll be looking at. You'll wonder where it came from. There's definitely, a mathematical foundation to everything that's in there. Anybody here use like Mathematica or MathWorks? Or is that thing by Wolfram? I think it's Mathematica, right? They give you, I had this kind of battle with tech support. They gave me this thing about finding the Hurst exponent and using fractional Brownian motion, and it was giving me numbers and I couldn't understand where they came from. So I said, what algorithm are you guys using? And they wouldn't tell me. I'm like, what's up with that? People actually like this? You know, and so they're saying, well, it's proprietary, sir. It's policy. And I'm like, I'm not going to use your code if you're not going to tell me how it works. I put stuff in, numbers come out, it's a black box, you're not going to tell me how that works? And they're like, no, sir. And I'm saying, okay, well, I guess I'm just not going to use your code or teach with it, because how's anybody supposed to, like, learn? So when I do these sorts of things, I give you all the code, tell you how it works, document the crap out of it, and sort of say, hey, you know, I'm letting it all hang out here, and if it's wrong, you'll tell me. And that's very important because anybody can make a mistake. So that's one of those things where I kind of felt like it was really important for you all to have access, total access to the code, and know where, you know, that code is coming from. You know, the Mathematica guys, they don't do that. I don't even think the MathWorks people do that with their toolbox. You know, they give you these M files and they say, that's it, you're done. Figure it out yourself. I'm like, I don't think that's correct. The other thing you'll find, and this is kind of important, if you get to a toolbox like MATLAB, they are not going to scale the output of a Fourier transform by dividing through by 1 over n. That means that all of your filters have to be divided through by 1 over n before you multiply them, or else all your numbers are going to be out of scale. Now they do that because they want their Fourier transform to run as fast as it possibly can, and they do not want to spend time dividing through by n. And the same thing for the Mathematica folks, and same thing for the Maple folks. And you know, it's really important that you guys know before you start using that stuff. It's garbage in, garbage out. If you put the stuff in and it comes out of scale, you're not going to know why your numbers don't work. And so I say, look, these are unitary transforms. You've got to divide through by n. It's part of the cost of the transform, even though it's a constant time operation or linear time operation. So I've argued with students about that. Well, that's what MATLAB told me, and it's correct because MATLAB said so. I'm like, no, it's not correct because MATLAB said so. It's wrong, and the reason why is this. It takes a lot of convincing to convince somebody that MATLAB is just wrong, and Fourier transforms need to be scaled. Then there's this other thing which you may have noticed about windows, and Brian was asking about windows. A window is an amplitude modulation on the input signal. That's in the time domain. So what you're doing is you're taking the string of numbers and you're sampling the amplitude so it doesn't have a sudden onset. That sudden onset of amplitude creates all kinds of spectral artifacts. And so what you try to do is you try and create an attack, a decay, a sustain, and a release amplitude envelope. And so the envelope generator that you use is called a window. And that window, and we talk a little bit about this in the book, that window is generally expressed as a windowing function that ranges from 0 to 1. Here's another reason why you have to scale all of your Fourier transforms. So with the amplitude coming in ranging from 0 to 1, then what you got to do is you got to figure, well, what's the right windowing function? And you can write your own, for sure. I've written my own. I think I called it the lion window, because what else? And I used, I think, what's called a quintic polynomial. Quintic polynomials are kind of fun because you can take a derivative like 5 times and you can make it so that the second derivative is 0 at the endpoints. So with the second derivative being 0, that gives you what's called a Gaussian curvature, which is 0 also at the endpoints. And having a Gaussian curvature that's 0 at the endpoints is the moral equivalent of making sure that your front wheel angle on your car is aligned with the wheels at the end of a maneuver. So if you're thinking about a car and you're thinking about parking, then what you do when you pull into a space and you're done is you leave the steering wheel parallel with the rear wheels. And so that's that's kind of like the Gaussian curvature of the trajectory of the car as it pulls into the space. So quintic polynomials allow you to do that. They give you the control over the endpoints. They give you the control over the derivative at the endpoints, and they also give you control over the second derivative at the endpoints. And once you have those things, then you can basically have good control over your window. And so that's why I went to a quintic polynomial. There are a couple of other windows. Some people use a cosine curve. That's infinitely differentiable. So they use that when they multiply, and that's not a bad curve. Other people use the Hanning curve. And what these things do is they concentrate the energy into the buckets, and they prevent what's called spectral leakage outside of the buckets. Now, spectral leakage, that's when you take a bucket and sample some energy, and a lot of the energy ends up in the adjacent buckets. And so you're not able to determine exactly what the frequency is. So Hanning windows essentially, or any kind of window, its goal is to try and reduce what's called the spectral leakage. In the world of Java, I think what we do is we give you a whole series of window classes. And if you go into the I think it's the MAT1, but I'll just do a quick search to make sure. Find in path Hanning. Yeah, it's under the MAT1. Make Hanning. So what we'll do here is we'll run that make Hanning as an example in MAT1 and see if we can get that to work. Yep, there it is. Hanning window. Pretty cool, actually. Looks nice. So what happens when you take the Hanning window and you multiply it by some kind of input signal is it shapes that input signal, and it makes it sound so that as though the volume is being turned up until it peaks and then being turned down until it's at a minimum. Let's see where that's being used. Gesundheit. So here's the Hanning window in action. Someone's passing in a double precision number, and they're being asked to graph the power spectral density. The input signal is being truncated to an integral power of 2. So instead of padding, what I'm doing is I go to the closest integral power of 2 of d that I can, and then truncate. Then I make a little Hanning window of the same length. I can make Hanning windows of any length I like. I'm going to do the entire thing all at once. Then when I want to window the input signal, I'm basically doing a piecewise multiply of each sample times the Hanning value. Then I take a fast Fourier transform instance, and I proceed to do what's called centering. Centering is a process whereby you take each input sample and multiply it by +1 and then -1. So you go input sample I, where I is equal to 0, you multiply by +1, and that doesn't change it. Then you go to I equal 1, and you multiply it by -1. And you go to I equal to 2, and you multiply by +1. And you go to I equal to 3, and you multiply by -1. That sounds like something really screwy. Why would anybody want to do that? And here it is, multiplying by +1 and -1. Isn't that weird? Why would anybody do that? And the reason why you do this, right over in here, is it allows you to center the output of the fast Fourier transform. Centering, normally what happens is you want to have the DC component in the center of your Fourier transform. But what happens when it's not centered is the DC component gets distributed to the edges. So the centering process moves the DC component so that it's in the center, and then you have 0 hertz right at the center, and you can see how much DC offset there is. And then as you go further and further from the center, you go higher and higher in frequency. That's what centering does, interestingly enough. We haven't talked much about centering. Then I do my computation on the, I'll call it the forward fast Fourier transform. And then over in here I did a bandpass filter between a low frequency and a high frequency. I can just take anything that's below the low frequency and set it to 0. Anything that's higher than the high frequency, set it to 0. That's what you call a bandpass filter. And then I can put in some kind of squelch if I want to reduce noise, because I got noise on the input signal and I know what the noise power is going to be. And then I can do an inverse fast Fourier transform and get the original signal back, which is pretty cool actually. So what this is doing is bandpass filtering, then it's removing noise, and then it's giving me the original signal back. That's pretty cool, come to think of it. We should run this graph PSD. So, what about that Hanning thing? How do we justify using Hanning? And where's that centering come from? Lots of new ideas. Probably should talk about that a little bit. So here's my API for doing Fourier transforms. Let's just zip through that. We've already seen the basic discrete Fourier transform, so that's okay. Guess that's all been done. But here's the FFT. And remember, these FFTs require that you have integral numbers, let's see, an integral power of 2 number of samples on input. It's a requirement. So taking log to the base 2 is one of those common things to make sure you know how many bits you need. How do you take log to the base 2? I got a calculator here, right? Calculator? You have calculators here? Here's a calculator. Alrighty, where's log? Shoot. It doesn't do it. Well, if it doesn't do log, we're screwed. Programmer? Scientific? There we go. So here's log, but it's log base 10. Oh, here's ln, but that's log base E. Yep. So if I got 1024 and I take the natural log, or it doesn't matter actually, take log to the base 10 and then divide through by 2 log base 10, I should get a number, and it's 10. So if I want log to the base 2, just take log to any base of the number and then divide through log to the same base of 2, and you'll have log base 2. In fact, you could take the log to any base. And that comes from the laws of exponents and the laws of logarithms. You guys know about those things? Laws of exponents, laws of logarithms? You've had that, right? Basic sort of stuff. I could probably find a convenient way to review it for you if you needed it. logs. It's log, log, it's big, it's heavy, it's wood. It's log, log, it's better than bed, it's good. You better get your log. Everyone needs a log. I'm going to get your log. It's log from Blammo. So here's a log. They have a Civil War log that comes with a saw, and you just can saw off the limbs. There's the log says that if I take the log of a to the y, it becomes y times the log of a, right? And so eventually the logs allow me to make these sort of interesting claims, right? Log to the base 2 of x. Yeah, I get that if I have 2 to the 10. But what if I want log to the base 2 of an arbitrary number? Let's say log to the base 2 of 4096. This is kind of what I was driving at before. So now I want to say, well, gee, log of 4096 is equal to y times log of 2, which is good. I solve for y, and now I have log of 4096 over log of 2, and I get a number which is like 12. So that comes from like exponents and law of logarithms. In fact, if you think about it, I can get log to any base just by dividing through by ln of the base for that number. Logarithms. And so now I can generalize it. If the base is b, then log of any base in the denominator will give me log to the base b. Right? That's kind of what I just said, only printed nicely. It's good to print it nicely. So the laws of logarithms give us sort of these ideas that you can take multiplication and turn it into addition, and division gets turned into subtraction, and exponents get turned into multiplication. You've seen this junk before. Nothing new here, but it's good to sort of just say these things because it refreshes your brain with the stuff that you probably haven't seen in a couple of decades or something. And why are we talking about intermodulation noise? Oh, that's actually interesting. Have we talked about frequency shifting in Fourier transforms? Not really, right? A lot of times what happens is people who are in the signal processing world like to talk about modulation. Modulation means taking one signal and using it to alter another signal. Sometimes in the Fourier domain, when you're in the frequency world, you can change your frequency by moving the contents of the buckets. So if you want to, let's say, let's assume the DC component is in the center. If you want to shift the voice lower, all you have to do is take all the buckets and copy them so that it's lower. Then when you do the inverse Fourier transform, your voice will sound lower. And if you want your voice to sound higher, you can take all the buckets and shift them away from the center, and then the voice will sound higher. Well, there's another way to do this. It's called ring modulation. And with ring modulation, you can take an input signal and then your modulating signal, and then what you're going to get is two subbands. The upper subband, which is the frequency of the carrier plus the modulating frequency, and the lower subband, which is the frequency of the carrier minus the modulating frequency. These two subbands are what are referred to in, I guess they call it CB. Anybody ever have a CB, a walkie-talkie, or ham? Well, ham radio is different. They have double sideband modulation. Some people call it amplitude modulation. Amplitude modulation is a form of double sideband modulation. There's an alternative where you only keep one of the sidebands, and that's called single sideband modulation. So if you were trying to do something at, I don't know, 2 gigahertz, right, you could take that input signal, use what's called a ring modulator, and the input signal might be, let's say, at 1 gigahertz, you could take another 1 gigahertz waveform, multiply it, and you could get 2 gigahertz out and 0 gigahertz out. So that's kind of cool. And your ring modulator could be something as simple as a ring of RF rated diodes. Let's see now. Crosstalk, I don't think we want to talk about that. That's too exotic. Channel capacity, we won't talk about that. Sorry, got off track. So let's see, what else can I do about this? So we did our, we've done the simple discrete Fourier transform, but now we've got the fast Fourier transform. And the fast Fourier transform examples that I can bring for you are the ones that are here under IACT20131028. I've got a nice test function here. And what we'll do is test suite. Wow, that sounds fancy. I don't want to do a test suite. So here's a an FFT, and I don't know if you recall, we did a ramp before with the DFT, but now we're going to do a fast Fourier transform. Let's see if this works. Oh, it just asserts it to be equal. If it's equal, then it worked. There has to be like a main in here somewhere, right? F3 to search from top. F3. No, that's it. So for me to run this main, go change this to main, hit run. I think all it does is assert true. I don't print any answers. I really want to print some answers. Let's see, what does this buy me? Alright, here's what we'll do. C dot, is there like a print in here? Yes, there is. Let's see if we can print it before we do anything. I'm confused. Where did the printing happen? This is like running, right? System, out, Control J, enter, test. This should like print test. It's not printing test. What could possibly be wrong? Here's a main. Oh, it's not public static void. Public static void main. It's still not printing test. Well, oh, it's running test get data. I think it's running the wrong thing. Let's just make sure this is working, because I got a little confused. Oh, thank goodness. Thank goodness something is working. Now why didn't this main over here run? I'll just copy it, because for some reason it seems to be in another part of the code. Copy. Paste. Run. Bear with me a minute. Oh, thank goodness. I don't know what the heck was that. What was that about? So here's a ramp, 0, 1, 2, 3, 4, 5, 6, 7, moving up after normalization. Then what we'll do is compute the forward Fourier transform. So that's good. We got something output. And now what we'll do is we'll compute the backward Fourier transform. Hope it comes out the same way. And that's in place. So an in-place Fourier transform is reusing the complex numbers which are being used on input. So you can basically say it's not allocating any new storage after the Fourier transform is done. So now here comes the backward FFT, and he says 1, 2, 3, 4, 5, 6, 7, and the complex components are infinitesimal. Alright, these are relatively small numbers, close to 0, which is essentially what you want. So you're basically starting with 1, 2, 3, 4, 5, 6, 7, 8, and you know what you can do before you normalize these things is you can print it. So you can print it right where it's at the ramp. Because this scale, the 1 over n part, was so important for us. Let's see now. Here is the ramp. What we'll do here is prior to scaling, we'll print it. So this will be S out, Control J, enter. This will be the start data, end quote, end paren sem, c dot print. And then what we'll do is we'll do a scale. We'll do the forward transform and print it. Then we'll do the backward transform, and we should get back to where we were. And let's just make sure that's true. So we started with numbers 0 through 7. We had these, this is the output of the forward Fourier transform. And here's the output, 0 through 7. So that's really close. In fact, now the next question, of course, will be, how much faster is a fast Fourier transform than a discrete Fourier transform? You can't benchmark something effectively with only 8 samples. You have to do it with a lot. Right? Well, 8 could be replaced with / pick a number, 20. So what that is 2 to the 20, which is like 1,000,000. Yeah, what that does is it takes 1 and shifts it over to the left 20 times. If you like, we can do something like this. S out, Control J, enter, quote, n equals, end quote, plus n. Oh, n. Does that not work? Oh, yes. So then hit run. Oh, I forgot. We're printing a lot. This is probably not the best idea I've ever had. Assertion failed. I guess I didn't get exact equality here. Let's start by not printing every single thing here. That's probably not necessary. And then as far as the assertion equality is concerned, let's take it down a notch. And now let's hit run. So here it is, 2 to the 10. Now let's bring it 2 to the 20. And 2 to the 10 was fine. 2 to the 20, maybe you had some issues. You know, I have a feeling we had some floating point computation problems, but this is what 2 to the 20 is supposed to be. Is that like a million? 1,048,576 is like a million. It's got to be an integral power of 2, so it's not going to be exactly a million. So where did we go wrong? 2 to the 15? Will that work? That's interesting about how the assertion of equality failed. So 2 to the 10 was fine. 2 to the 15 had a problem. 2 to the 12? So 2 to the 12 worked, but once you got really large, things started to fall apart a little bit. So then the question, of course, becomes how long would it take to do a number like 2 to the 12 with a discrete Fourier transform? You could see it was running really fast here. And even 2 to the 20 was pretty good. So now if you wanted to, you could find a discrete Fourier transform. Here's one called DFT. Let's see what test DFT 100 does for me. It's graphing a lot. I really don't want that graphing to get in the way of my benchmarking, but we'll just do 100 elements. That's not too bad. Nice and fast. Did it do 100? I don't actually think that did 100. Oh, it only did 16. So let's do 2, I know, 1 to the 8, that's 256, right? See how long that takes. That's fast. Now let's do, what did we do? Like 12? You see now it's printing everything. But check out how slow it is before it actually starts to print. Slow, right? Now let's do 2 to the, what did we get up to? Like 15? Or 20? So now it's a yawner. Right? Now you're seeing the tyranny of the quadratic complexity in terms of the DFT. Now you could say, but there's you're trading space for time because you don't necessarily have to have, you know, all the complexity of an FFT in there. And I could say, okay, yeah, sure, but at some level one has to draw the line, and here's where you do it. Once you start to get into these really big sequences, these things take a long time. And the question of exactly when it's worthwhile to do an FFT versus a DFT is different for every CPU. Sometimes very fast CPUs, it doesn't matter. If you're just doing a short number of samples, your FFT is not needed. You don't need that complexity. But here, you know, if you think about it another way, DFT needs complex numbers too. And this is still not done. And it's still hanging out, waiting for completion. And it could take a very long time. And so that kind of makes the point. That if you want things to run in reasonable time, you know, either shoot for really short samples like that and say that's fast enough, or maybe switch over to an FFT. And also keep in mind, you know, when you're starting to sample at higher sample rates, the total number of samples you're trying to sample could be quite large. Do we need a break? It's feeling like break time. Okay, let's stop for now.